In-CAD webinar. We're going to be discussing drop testing your design in Nastran In-CAD. Bart McPheeters will be presenting, and I will be playing devil's advocate, trying to squeeze a little bit more information out of him and ask any of the questions that you might have for him. But before we start that, I want to run a little poll here. Some basic questions to see how long, to get to know you as our audience, to see how long you've been using In-CAD or simulating. So if you would take a moment just to vote here quickly. All right, it seems most of you have voted already, so got some last minute votes. All right, we'll move on here to the share that. So it looks like we've got a majority of people here are less than a year, and kind of a chunk that's been more than 3 years. One more question. Is Nastran In-CAD your primary FEA simulation tool? All right, looks like we've got a majority of people here who voted already, so let's see what we've got. Looks like Nastran In-CAD is new for you guys, so great. That's wonderful. We'll be providing lots of new information. Bart, if you could bring us into the news here.
Okay, I can do that. I think I can do that. There we go. Now we're there.
All right, thank you. So recent webinars, recently me and Bart did common errors messages in Autodesk Nastran, and and previously to that we've done how to identify good mesh in Nastran In-CAD. The picks and clicks are specific to Nastran, but the knowledge there is generally applicable to pretty much any simulation program. We do this live. This is a live presentation. We do this bi-weekly. It's about 20 to 40 minutes long. There are plenty of places to sign up. So if you know anybody who has not heard about it yet, please let them know. We do upload our videos to YouTube afterwards. Bart, next page, please, sir.
Okay. There we go.
All right, news, not so much new news, mostly the same news, but if you haven't heard, Hotfix 1 for 2016 has been released, and we do have some new training for In-CAD. You can download it, but you can follow the link here in this page. This presentation will be available on our Autodesk, on our box share account, so you'll be able to download models, the PowerPoint here. And if we can go to the next tab page, Bart, please.
Okay, should be there.
Thank you, sir. So, most recent articles. So, as you may know, whenever you call in, ask for support, we document all the issues that we find, fatal errors, how to install the Nastran In-CAD help documentation locally. You can find all of this by going to knowledge.autodesk.com. You can search for information, just type it in there, search. You can filter it down to whichever product you're looking for. So I highly recommend to use that, because when we are documenting all situations that we run into, hopefully it will be worded ideally it'll be worded in a sense, it'll be worded in the way that you would be searching for.
You always hope that makes it easier to find.
Yes. Next tab, I think this is it for us for news. All right, so as I mentioned before, today's presentation is going to be on drop testing your design in Autodesk Nastran In-CAD. Bart here is going to be our main presenter. I will be fielding questions for you and trying to squeeze out a little bit more information, and hopefully we can try to stump Bart this time. I think we were semi-successful last time. We got one stump for you, right, Bart?
Yes, indeed. Yes, indeed. You got one that
All right,
has
all
like
right.
the.
So please ask your questions because it's fun to stop Bart.
Okay. Also, notice down below there's a link to the download for this presentation. Since the download link is actually on the download, it's hard to find it if you don't know where it is in the first place. So you may want to write down that little download link.
Ah, good
Okay.
point. Yes, right. Bottom of
Yes.
this page.
Yes, it's available for download, but if I don't know where to download it, I can't download it. So putting it in the, it's like, what is it? It's like packing the crowbar in the crate. Okay, so we'll get on here with the drop test simulation with the funky graphic of a city in the background. I'm going to do a couple things here. I'm going to do sort of an introduction to drop test simulation and what you need and what goes on with it. And I'm going to describe two different ways to do drop testing inside of automatic, or drop test simulation inside of In-CAD. One is the automatic way, which is really easy and fast, and the other is the manual way. So I'll talk a little bit about what those two are and how they work. And then I'll sort of show you all these with little pictures of all of this. If you're going to do a drop test, or actually you can use this for an impact test just as easily, but if I've got my object up here, the blue box up on top, I need to know what I'm dropping. I need to know the floor down here, what I'm dropping it into, or if this is an impact test, I need to know what it's running into. I need to know how high it's dropping, the little H over here. If it's free fall dropping, I need an acceleration of gravity. If it's an impactor, I don't necessarily need to know that, in which case what I probably need to know is the initial velocity, which is up here, the initial drop velocity. So there isn't a whole lot that you need to know in order to do a drop test. It's a fairly basic set of things. And again, if I'm doing an impact test rather than a drop test, I see, I'm throwing something at something, and I have a little example I'll show you of that where I'm hitting something with a hammer. You generally don't have the acceleration of gravity, and instead you have an initial velocity, and you may not have a height because you start it. But anyway, some details. When you do these animations and you see people doing these simulations, they always have this picture of this thing dropping down and hitting the bottom and bouncing away and breaking and parts going out. And all that free fall looks really good in a plot because, people think you're drop testing. But from an analytical point of view, there is absolutely nothing happening except that it's moving through space. There's no stresses, there's no anything. So in most cases, when you want to do some kind of an impact or a drop test simulation, what you do is you move your object from its lofty position up here, where you have a height and a gravity and a velocity, you move it down to where it's just about to hit or hitting or just touching, and you calculate a new velocity. If I'm doing a drop test, it'll be the initial velocity plus, 1/2 GT squared or something. I can figure out what it is. So I now have an impact velocity. And the other thing to note is that when this hits the bottom and bounce up, this is a contact, and it's separation contact, and it's a nonlinear phenomenon because we have a boundary condition change. Now, there's certain situations where you can pretend that it's in contact and do it without actually going the nonlinear route. But most of the time, what you're interested in is the interaction of the two parts and how they bounce and hit and twist and rotate. And that becomes a nonlinear phenomenon. The other thing to note is that when I'm running this, I'm running it through time. So after it hits, I've got a time-dependent analysis. So drop testing is a nonlinear, and it's time-dependent. Those are sort of important things to consider. So the way it's actually done is with a nonlinear transient analysis. The transient gives you the time dependence. The nonlinear gives you the ability to have contact. Depending on what you're dropping and how it reacts and whether it spins out of control after it hits, you probably have large deformations. And so if I drop something and it hits, it's going to bounce back up, depending on what you're hitting, It's going to bounce back up, or it's going to ricochet, or if I'm throwing something at something else, it's probably going to deform large, which is again another nonlinear capability. Also, when I end up doing drop testing like this, very often we're looking at post-yield or post-failure of our materials. People are looking, drop testing is often sort of a worst-case scenario, and even if you're drop testing things that shouldn't be breaking, you're often allowing some things to break in order to do it. So you possibly have nonlinear materials. It's probably even more probable that you do, but you definitely have contact. So this nonlinear transient is what you get. Here's a little plot of one of the ones that I'm going to show you here. And in this one, this is the impact point displacement. So it hits and it compresses a little bit. And I started with a drop height of about, I don't know, 13 inches or something. And so it compresses a little as it hits, it bounces around a little bit, the natural frequency of the structure vibrates, and it starts popping back away, and the whole thing flies off into space. And most of the stresses and the interest are going to happen at the impact point, but occasionally this particular one doesn't rotate, but often when you do a drop test, it'll hit one corner, and that corner will rebound, and then another corner will come in, so you'll have another point that starts up here and moves down and hits on its own. So you can get some complicated, large deformation behavior out of it. The other thing to notice is, and I'll show you a little bit more, is that this curve is sort of noisy, because when you drop test something or you impact testing, you sort of excite a lot of natural frequencies in the structure, and things aren't necessarily clean. It's not, if I push something slowly into a wall, it sort of hits the wall and it's all in contact. But if I throw it, it tends to hit and bounce and vibrate a lot, and it excites a lot of high frequency dynamics in my structure. And so in this one you can see these little waves in this curve, which are in a large part the natural frequency of the structure at that point that it hits vibrating. So often you'll end up with multiple hits. It hits it and rebounds a little bit. The natural frequency causes it to rebound and hit again, and sometimes you get a number of times where the thing actually impacts. So instead of one clean impact, it's multiple ones. And that's just a function of the way drop testing and impact work. So as I mentioned, there's two ways to do drop testing. There's what I'll call the automatic way, or the easy way, and it uses the Autodesk Nastran In-CAD Automatic Impact Analysis. It's a separate little menu, and I'll show you what it is and where it is. It's very, very easy to set up, but there are some limits to the capabilities and limits to what you can actually do with it. Some of those limitations and things we're looking at removing in future releases, but at the moment I'll talk about what those are. The other way to do a drop testing is to forget the automatic stuff and just manually set it up yourself. Set it up as a nonlinear transient analysis, manually set up the velocities, the contact, anything else that needs to be set up. You can manually set it up. The advantage is you get a little more control over your solution. You have a wide range of capabilities that may or may not be available to you in the automatic impact analysis. So here's our little thing. This is not the one I'm going to demonstrate, but this is one I've got. This is really, as we showed earlier, what you need to know. You need to know the falling object, the path that it's dropping on, how fast it's dropping, and while you don't necessarily need something for it to hit, if you don't have something for it hit, it'll just fall off into space and go on forever. But generally, this is what you need. You need to know where it's going. So in the automatic method, it's a very simple form. You get to pick the projectile body, in this case the headphones. You have a projectile path, and generally what we suggest is you take a point roughly where it's going to first impact and draw that line down to a point on whatever it's going to hit. Now, this impacted body down here, in this case, I think I had forgotten to constrain it, so when I ran this analysis, the headphones ran down, hit this, and then this sort of flew away and the headphones went back the other way. So it was more of an impact than a drop test, but it can be done. I was just letting this go and dropping it, so I had an initial velocity of 0, and I had a 1G in US units, 386.4 to drop it. So those are the little things that you put into the impact analysis, and you say, okay, done, zip, go, and that's really all there is to it. So I'm going to do a little show you this and show you some of the stuff that comes out on this. Here's a little part. I've got a little shelf sitting here. It's a little wall shelf here, and you can see I have created a little sketch path here, and it took me a while to figure out how to best to do this. But this is the path that it's going to fall on, this little line here. And what that is, has to be is a Inventor 3D sketch, a 3D sketch line. And so it has to be in the same part as the thing you're dropping. So I don't have it open, but when I go into Inventor, I'll open up this part to edit it. I'll create a sketch point down on the plane here, and then I'll connect my impact point to the sketch point down here with a 3D line or a 3D sketch line, and that becomes my path. So that's really all there is to set this up, is I need that in the geometry. This particular plate I constrained so that when I hit it, it's going to bounce around and do some cool stuff. And it isn't exactly straight, the drop, but I'm not very good with Inventor itself, so I was having a little trouble with that. But anyway, the analysis up here isn't so much where you do this. Normally I would go into this and I'd say I want to edit it, and I'd pick my type up here. But you notice none of the types up here are drop test or impact analysis. So what you really have to do instead is right click up here, and there's an item down here that says solve impact analysis. And this is the automatic impact analysis setup. So if I pick setup impact analysis here, this gives me that little form that you saw. And here is my part. Here is my sketch segment that goes down. I put in 1G and an initial velocity. Now in this particular one, there's a little button here that says reverse direction. I had, believe it or not, drawn my sketch point the wrong way. So when I did it, it was going to drop up, which doesn't help anybody. So I created it and I reversed the direction. So now this point on the bottom is going to be one of the first to impact. This is a sketch point down on the floor, and this is my line. So really, that's all I have to set up to do this. There's some advanced settings you can set up. Honestly, I haven't really needed to do too much of this because most of these are set automatically. Actually, this is on by default. It's not off by default. It's doing a modal transient, but that doesn't even matter either. So there's not a lot that you're going to want to play with on that. These are the things you're going to need right here. So I'll give that a go. And then the run button up here again runs whatever you have set here. So when I actually want to run one of these, I go down here and solve here. And so I solve my automatic impact analysis using sort of off menu stuff. That may change at some point in the future, but at the moment, that's where it is. It's not here on the normal analysis form. It is down here. Now, the first thing that this is going to do is, because as I've mentioned, from here down to the point where it hits is largely, it's a trivial solution from an analysis point of view, but if we try to actually run it, Nastran will actually try to solve it. And it'll calculate it, and it'll calculate it, and it'll do it fairly fast, but it's a waste of time. So when you use the automatic impact generation, what it actually does is it takes the part and it moves it all the way down to this point where it's just about to hit, and it starts right at that point. So when I actually run my analysis and get my results here, these are in here, yes, okay. I'll load my results in. You'll see that the very first time step that comes up here is, I ran it, it runs, and the number of time steps that it runs for is determined automatically. you have some control over it, but when you're running the automatic one. So at time step 0, if I plot, let's look at my shell von Mises to start with. And it's always important to do actual deformations on nonlinear analyses. So at time step 0, there should be no loads or no anything at all. Yeah, and it's all, you can see the magnitude of the stress is 10 to the minus 10th. So nothing's really happening. But on the very first time step, suddenly we have an impact. And this is suddenly impacted. You can see suddenly we're starting to get some stresses here. And as you sort of work your way up these steps, oh, look what I'm looking at. I'm looking at the wrong thing here. Oh, geez, how'd that happen? Let's go back to my shell. Where are we? Shell Max von Mises bottom top. Let's find that one. Do Max principal bottom top. That's close enough. Okay. Let's look at my shell first place. Okay. So back here again on the very, very first time step, the shell is 0, as you'd expect. But as soon as it actually does anything, it's actually hit. And by the time we get to the third time step, you can start to see where it's really hit and it's really starting to impact. And as you progress through time, you can see it hits, and by now it's rebounded. So at this point, it's rebounding off, and this is all only time step 8. And so you can sort of watch a progression of stress waves coming and moving in and out and flying away as you do this. I can do an animation of this. I'm not going to do it right now, but I can do 10 frames. I can do a full thing and do a multi-set animation to do this. And that lets me do some cool things and animate, and I can watch the stress waves moving around. They take a little while to generate, so I'm not actually going to do that right now. The other thing I can look at is I can go into my contour options and tell it I want to look at, say, let's do this right, the solid von Mises stress, for instance. How about solid von Mises stress? Now with the solid ones, the shell itself isn't doing anything, but I can see what happens with my part as I walk through time, because initially the stresses are fairly low when it hits. Oops, let's go back up here to where it hits here. And so the stresses are pretty low when it hits. And as it bounces off and it gets fairly far off in the thing, the stresses actually drop down a little bit. If I'd left plasticity in, you'd see some. But this is sort of vibrating now. It's vibrating as it flies along, and it's vibrating. Oh, my deform options should be. What did I got? I'm not sure why that's showing that. I don't know what that's doing. It works just fine. Oh, it's rotating. That's what it is. But anyway, okay. So those are the kinds of things you do. The other thing you're going to get out of this is a whole series of XY plots. And one of the ones that's always looked is like maximum displacement versus time. And so you can look at something like that. It's a maximum displacement versus time. Or I can look at a maximum linear acceleration versus time. Notice the acceleration, we're seeing a lot of this wiggly stuff. And that's because when I hit this, it vibrates and it starts shaking. And so the maximum acceleration is a really noisy plot. The maximum linear velocity here is going to be sort of noisy as well. And the maximum displacement, I'm not sure what that's doing, but anyway. But I can create a plot down here if I want to do this. I can create a new plot and call this the impact point, for instance. And I can go look and pick this point where it's hitting up here. Let's get this and zoom in so that I pick the right point. So I can pick my ID here to be this point right here. Yeah, 2534 is the right one. And I can show my XY plot of it. You can see what it's done is its deflection starts at about 13 inches up here. And that's because the zero location of the point was up where it dropped. So it starts at 13 inches, the analysis where it hits, moves down a little bit, and then starts shaking and vibrating as it goes away. So here it really starts moving away, so you can see that. And again, if I change this from displacement to linear velocity and look at my plot, it's a lot noisier. And this is fairly typical of any kind of impact analysis. You get a lot of this noisy natural frequency stuff. So people often filter the results, and I always sort of feel silly filtering the results of an analysis, but it's sort of what you have to do. Okay.
Well, to interject something there real quickly on that, if I recall correctly, if you were to perform a fast Fourier transformation on that, you could actually extract the natural frequencies of the model.
Absolutely.
What it's vibrating at, that noise is the natural frequency of the structure itself.
Absolutely. And depending on what kind of damping you've put into this analysis, you'll be able to see the high frequency and the low frequency ones, and you'll see high frequency things often damp out faster. So you'll see a lot of high frequency noise that'll get smaller and smaller, and you'll be left with the low frequency noise. I always like to look at when we do, I used to do a lot of shock test work with ships. And when you hit a ship with a shock wave, like from an underwater mine or something, what you'll see is you'll see a lot of high frequency noise as the panels of the ship go shaking around like crazy, and then they all damp out. And what you're left with is the natural frequency of the whole ship vibrating, which is a much lower frequency and takes a lot longer to damp out. So yeah, an FFT, a fast Fourier transform, will show you all the natural frequencies of this structure that you would get if you happen to hit it with a hammer at that point. So it's sort of a way to extract natural frequencies. And you should see it, which is, and this also lands into something that I always tell people. Even if I'm doing a static analysis, I always start with a natural frequency analysis, because then I know what I'm getting. So when I go over here and look at my linear velocity versus time and I see this noise, I ought to know what frequency that noise should be. And I can go in here and I can count peaks and sort of calculate it and figure it out. And if I run it and I get 10 hertz and I calculated it should be 50 hertz, I've probably done something wrong. So there's a lot you can be gained by looking at the outputs on this. It automatically generates a lot of stuff. Component 1 displacement, it doesn't displace very far in the one direction. Component 2 displacement, that's the big one, that's where it bounces. Component 3 probably doesn't. Oh, component 3, interesting. Component 3 is the Z direction, so that's side to side. So this has a fairly defined frequency side to side when it gets hit in the vertical direction. So you get some interesting things out of these and interesting plots out of something like this. So anyway, moving right along.
Well, I have another question for you, sir, regarding
absolutely.
the initial setup there.
Okay.
So you draw the line, which can be the vector of your path. So you don't necessarily have to drop the thing straight down. It could have some lateral movement.
Absolutely.
But what if you were trying to be smart and you put in the initial velocity and you already have your thing drawn really close to the impact object? Would that still function properly? Because I mean, obviously here the program takes care of closing that distance without having to solve it,
right,
and finding the initial velocity. But what if you were doing it yourself? Would that function just the same?
It would. If there's no room to draw this line, then the automatic setup isn't going to really buy you much. And that's sort of a good segue, because if you are already in that situation, let me do this, you may be easier to do it in the manual method. And with the manual method, we drop using a nonlinear transient analysis. We're not using any of the automatic stuff. We need a lot of stuff to set up the model, but again, it's not all that hard to do. You have to, with the automatic setup, it identified the two bodies and created contact between them. And so it ran and did the contact between them. So my contact has to be defined, and unless I have a zero gap, I probably don't want to use automatic contact, because automatic contact is really good for finding things that are right next to each other, but it has a very hard time when they're not quite. And besides, I prefer my, automatic contact anyway. Drop testing there aren't that many places that are going to hit, so defining it's not all that hard, and I'll show a little example. In order to do it manually, here's the second condition, which is just what James pointed out. The part should be located very close to the impact point. I'll show you that. And rather than drawing that line and letting it calculate the initial velocity from, what is it, 1/2 ag squared, at squared, 1/2 gt squared, that's the right formula. Instead of doing that calculation, you have to do the calculation yourself and set that initial velocity. And then, of course, it's a nonlinear transient, so you have to set up the time steps and the duration, and any of the nonlinear iteration settings that are likely to come into it, you'll need to play with as well. So let me do sort of quickly here another little demo model here that hopefully everything has worked. Here's a different one. It's the same stupid little shelf. This time we're going to simulate it's getting hit by a hammer. The shelf has these 3 holes back here, and bolts go through those, and those hold it onto the wall. And so, you know, this is someone stepping on it or someone whacking it with a hammer or something, and we happen to have a hammer model sitting around, so we decided we'll hit it with a hammer. So we got a couple things to do. The first thing we need to do is the contact. So there's a contact we're going to set up, and one is the shelf where it's getting hit, and the other is on the contact, is on the mallet where it's getting hit. So that's pretty good. Now I actually have a small gap here, and when you run the analysis, what you're going to see is that it takes a little while. It takes a couple steps before it hits. And the other part of the reason that I had to do this is separation contact, because obviously they're separated and they can hit and bounce apart. But there's this gap here, and this gap is small, but my activation distance over here, I used an activation distance of 5 millimeters. And because my gap here is, I don't know, 2.5 millimeters, and so I wanted to make sure that these two surfaces actually recognize that they're going to come into contact. So I defined the contact, I gave it that. This particular model, actually, the head of the mallet and the head and the handle were actually 2 separate parts, so there's also a contact zone gluing the 2 of those together. So that was just another thing I had to set up. Okay, so I've got the contact, I've got the mallet. Now the other thing is I have calculated my initial velocity. So what I had to do this time is I create a load down here, and the load that I create is an initial condition, and the subtype is a velocity, and I picked the whole handle and the whole head of the mallet. Now one thing you may or may not have noticed is when you go to pick things, if you right-click in the Selected Entities window, there's a filter that lets you select faces, edges, vertices, or so on, but there isn't one for selecting whole bodies, which is what we need. So in order to pick this, what I had to do was go in and select it, and then hit right-click and say, oops, let me get in here. I'd go in here, and I have to say Select Other, and then I can find the solid in here, and it'll tell me, and that's the way I pick the solid body. So I want to make sure up here that I only have solid bodies for my initial velocity. The worst thing you can do is put the face of it with an initial velocity and the rest of it without an initial velocity. You end up with some really weird results where the outside skin goes flying down and hits stuff, and the rest of it gets dragged along for it. So I gave it 1,001 meter per second. Wasn't a particularly hard swing, and so that was my other thing. Now the other thing was I went up here. This time we're genuinely choosing nonlinear transient response. Large displacements are on because we're doing all this. And then we have a nonlinear setup here. When I've been doing these impact analyses, I'll often start and I'll run it for a while, and there's a little window that pops up as it runs, and it tells me what's converging and what's not converging. And in my experience with these, I've found that by default, load and work are what Nastran uses. Load doesn't often converge very well for drop tests, so it's probably not a bad matter of hand to change it to displacement and work and start with that. I don't have to put a tolerance in, it will use the default, but if I check these two, it'll use those. And if you watch the iterations go by, you'll see the displacement converges very quickly, and then the work slowly follows after that. If you put in load, it sometimes takes forever to converge. So that's just sort of a little tip deal. The other thing I have to do is I have to decide how long I'm going to run it for and what my time steps are. The automatic method actually picks this for you based on natural frequencies and all sorts of stuff and comes out and gives you a number. Well, if I've run a modal analysis, I know what the natural frequency, I know how fast it's hitting, I have an idea of how fast it might be and how long I want to watch it vibrate. So I chose in this case was a 1/10 of a millisecond time steps. I ran it for 100 of them, so I went up to a 100th of a second, I think, to see what this actually looks like. And at that point, that was really all I had to do. My load we saw, my constraint holds the shelf on, and then I used the run button and just ran it and ran off, and I don't think this is the results of this analysis. No, they're not. I don't have the results of this analysis, but one thing I found when I actually run this is this rubber mallet handle is pretty soft, and so when you hit the shelf with it, the mallet bends and you get a little crease in the middle of it as it folds itself around the shelf. And when you think about it, that makes sense. The other thing that I discovered is if you hit this shelf like this, you're not going to break the shelf off. What's going to happen is the bolts back here are going to rip out, which was sort of a surprise result to me. So, when you think about it, I think, how if I wanted to get this shelf off the wall, how would I do it? I might hit it with a mallet. So, made sense to me. So, this is just about all I've got here. Looks like the time is just about right here. I'll finish up here. And so, the question is, why use the manual way at all? The easy way is limited to a simple part. The automatic method, you can only pick one part at the moment. That may change in the future. My mallet here was 2 parts, so I couldn't use the automatic method. The hard way is required for multi-part assemblies, such as the mallet, or I have a game controller that I can drop test, or those headphones when we ran it with the automatic method, we actually merged them all into one part. So that sort of cheated. You also get more control over the analysis times. What you do, if you want to actually see it hit and rebound, you can start it a little bit before it hits. And so it gives you, and of course we used to joke that the automatic way is for wimps, but it's just an easy way to save time, so it's not really a way to do that. So summary, you got a single part, the part's not located near what you're hitting, automatic way, that's the way to do it. You got a multi-part assembly, you want to do a little more control over, go with the manual way. And just for the record, the manual way is actually what the automatic way is doing in the background automatically with the automatic impact analysis. So when I choose the automatic way, if I look at my data deck, the data deck looks like a nonlinear transient. It looks like the manual method. So it's internally it's doing the same thing, even though it's a lot easier to set up. So the manual way, the automatic way for WIMPs is aside. If you can use the automatic way, that's really the way to go. So at that point, I think I can open up for any kind of questions people might have, including James.
We do have a question. Do you have to set up contacts for the automatic method?
Nope, they are automatically set up, which is yet a further advantage of using the automatic method.
So I'm assuming because you said it defaults to separation, correct?
Yeah, on the automatic method, it's always separation. And
All
actually, if
right,
you're
now,
doing impact, you probably want to do that anyway.
mm-hmm. So in your automatic one, we saw it rotate. It looked like it rotated and was penetrating through the surface. Is that sort of a limitation of the automatic way? Is it only takes the initial sort of contact?
Yes, and in some cases that's true. I'm not sure what happened on that. I'm suspecting that the data set that I loaded was the wrong one because
Okay.
I thought it creates contact everywhere, so you would get multiple contacts. Um, it may have been that the automatic contact determination distance was set too high, too low, and
Mm-hmm.
that's something you can tweak in the automatic method. If you see an automatic one where it does that, that's a tweak that you can do on the setup form. You can say use a, my contact distance is more than a millimeter. It's 30 millimeters, and it would prevent it from doing that.
Okay. What about time step control? Because the manual method gives you good time step control. So if you end up with kind of too coarse of a time step to really see what was going on, is there much control in the automatic method regarding that?
There's very little control, and what I'll tell you is, let me go back to that model here. When I actually run this model, if I go to my Nastran input file, let me regenerate it just for yucks here. The way contact is generated is with this impact generate entry here. And what it does is it leaves a little blank out here at the end. And it's calculating the time steps automatically based on the characteristics of the model and so forth. If I want to change that, I can go in here, and there's a little button here that says, where is it? Maybe I right click on it. Nope, nope, nope. Where's my edit card? Is that this
Oh,
the
you're still in
one?
the right click menu. That's why when you're hovering.
There we are. No, 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 no. It's collapse all, show hide, update Nastran. Oh, there it is. Insert new card, save Nastran file. I can edit. There it is. Double click on it. I can edit this entry in here, and I can go over here and I can just type in whatever I want to type in. And so I can type in my own time steps if I don't like what's there.
Okay.
The other thing that's in here is a contact tolerance that's defaulting, and I can put in a different time tolerance in here. The only issue is it does it for this, and if I go up here and say run my model again, it's going to create a new one of these that's going to overwrite my old one. So, ooh, don't want to delete that. But this is how it generates the automatic contact, and this is the grid point that's closest. This is default velocity. This is the acceleration of gravity. This is the vector that it's following. And then there's a bunch of stuff out here for the time steps that are defaulting, and you can change them. And it's not that hard, but it can be done. It's not that hard, but it's not all that automatic either.
I understand. Which then leads you to why use the automatic, use the manual at that point.
Yeah, at that point you're starting to think maybe I should be using the manual. Again, with the manual you have to pick the time steps and do sensible stuff and know the modal characteristics, but I might argue that if you don't know the modal characteristics in the first place, you probably shouldn't be doing a drop test. Which isn't to say that I actually did a modal analysis on this when I ran it, but that's just me being that's just me.
Convenience of presentation, basically. But
Indeed.
all right. Well, if we anybody have any questions out there, looking for more questions to ask Bart, we haven't stumped him yet, so please. I'm going to ponder here a challenging question for you, Bart.
Okay. And now the other thing I'll bring out here, I did this entirely using linear materials. So it's hitting here and it's bouncing off. The other thing I did was this plate down here, I modeled it as an actual plate so that when we ran it, you could see the deformations. If I just constrained all of the points on this plate it would effectively be a rigid plate. And so this would go down, it would hit a rigid surface and bounce off. That'll save you computation cycles. And if you've got something, this is plastic dropping on steel, I don't know how much you're going to get, how much deformation you're going to get and flexibility out of a half-inch steel plate. Drop a piece of plastic on it. So if you want to speed up the analysis, it might make sense to just constrain it all, and that way you've got a rigid surface that it's running into.
Mm-hmm. I do got a challenging question for you.
Okay.
Any recommendations on validating an impact model?
Oh, good grief.
Or...
I'll tell you what I do. I do a couple things. When I drop it, it's going to vibrate, and I will do that modal analysis, and when I drop it and I look at the transient results, I'm going to look and I'm do a hand calc. I'm going to count peaks and come up with a natural frequency, and the natural frequency that I see should be, when you run a modal analysis, we tell you what the modal mass is in different directions. And if I'm dropping this in the y direction, my part will have a number of modes that have high modal mass in the y directions. Those, especially the highest ones, should be the dominant frequencies in my response. So if I look at my output and it's not vibrating at those frequencies, then there's probably something wrong. So a quick modal frequency check is probably not a bad way to do it. The other thing is I'll plot the velocity. I know I can do a hand calc and tell it how fast it should be going when it hits. I can do a little, M1V1 equals M2V2. I should be able to calculate how fast it's going to rebound, roughly. So I can look at my graphs and draw some straight lines and make sure that my rebound is about right. And I can often do a hand calc for stress and get an idea whether the stress is approximately correct or not. And those are sort of things I do to validate it. One thing you'll always find is if you drop, if I've got a cube and I drop it on the corner and I don't include any material plasticity, you're going to end up with really, really high stresses on that corner that just aren't going to look right. But anyone knows that if you drop a cube, almost if you drop a steel cube on a carpeted floor, you're still going to dent the corner of the cube. So at that point, you really need some kind of plasticity. And again, look at what kind of plasticity you get. Because on drop testing, you almost always will have some degree of deformation at the impact point, just because it's an initial point. It's a very, very, very high, the whole weight, the whole velocity, the whole energy is concentrated at a single point. And what usually happens is it yields, and you end up with your little cube with little dinged corners on them. And your phone, if you're drop testing your phone unintentionally, you'll see little dents on the corners and little dings, and a lot of that is because you're going to see a lot of plasticity right at the impact point. So that's the kind of thing I would expect to see when I do a drop test. And I would ignore super high stresses at the impact point, but I would look at the zone of plasticity and see whether it makes sense. The whole model's plastic, probably doesn't make sense. No plasticity probably doesn't make sense. But if there's a zone that sort of corresponds with the feel, that's another way to validate, to get a feel for it. So those are what I do.
So I got a question for you now about so when you're basically looking at the vibration of the part after impact. You're trying to see if that matches up with your modal analysis. Let's say it doesn't. What would be the first thing that you would think would be wrong? Let's assume you have everything set up, distance, direction, all that. It matches correctly, but it's not quite right. What would be your first instinct.
I'd look at material properties, things like density.
Mm-hmm.
There's nothing, what's the density of steel? 0.283. Yeah, but that's in pounds per cubic inch. And so if I'm getting, and Nastran likes consistent units, so it should be pounds second squared inches to the fourth, per inch to the fourth, is the units that density should be in. So if I drop it and I'm getting, lots of plasticity and a really low frequency, make sure I have the right units for my mass. Make sure my units are consistent. This little shelf thing was killing me because I exported it in English units and I re-imported it into metric units. And
Mm-hmm.
I was like, what is going on? Because I had my mass was in metric tons and my distances were in inches. And because I had just totally forgotten to do it. And like I said, it was immediately obvious I was getting wrong answers. And so, my validations did not hold up. And, it turns out it wasn't that I had the wrong mass or the wrong anything. I had just totally hosed my units. It was pretty fun when my plate that I was dropping it on was 1,000 feet square. The little shelf's about a foot long. Let me tell you, it was quite the drop test. But a 1,000 foot plate with none supported that's a half-inch thick, it sags further than this falls. And then again, that was one that I caught that one pretty fast. But again, it was my little validations. And so that's the first thing I'd look at is units, check units. Do my units of my distance look right? Do the units of my density and my mass look right? Are my velocity and acceleration units consistent? I had a great problem with someone who was doing a shock analysis one time, and the paperwork located the explosive in feet away and inches below. And they had blindly copied the numbers and ended up locating the explosive inside the model, which was very spectacular watching a simulation of a model explode, but that was not what they were trying to simulate.
That sounds fun to me. I'd like to do that. Let's do that now.
It was very cool, but he brought it over and he says, you got to see this. It's totally wrong, but you got to see this. And that was, again, it was just units. It was what I had trouble with this one on.
Mm-hmm. Well, it's getting towards the end of our presentation here. Appreciate your demonstrations, Bart, on both the manual and the automatic way for drop test. We are also out of questions at this time, so if everybody doesn't mind, let's wrap this up.
Okay.
Anything in review you would like to mention real quickly?
No, just like I said, as James had pointed out, do some. I'm big on validate.
Thank you very much.
Yeah, validate your model. That's all I can say.
So last thing I'd like to point out is, once again, this video presentation will be available on YouTube, and you can download models and this presentation here at the URL listed below. That's autodesk.box.com/Nastran In-CAD IQ. Thank you, everybody, again for joining us.